last time. We were projecting into the last page.
Oh, projector room 1.5.
No, it seems to be on.
Oh, something is different. Yeah. There's no signal.
Let's see. Are you sure it's?
5.5. This is 1.6.
Oh, I see. So maybe we'll try. Can you try your laptop? Okay, that works. I guess, do you need your laptop?
Yes. I need my laptop. What's happening? Why is your laptop not on? Maybe you need to be logged in. You know what? Get online. Get online. But I
Well, I guess I can just go without the projector.
Does anybody want to volunteer their computer? But you need your laptop too.
No, I just need the book.
For some reason, it doesn't work with this computer.
Anyone? Oh, I see. I'm connected to the visitors.
Oh yes. Let's try it again. Oh,
Okay, cool.
so why is your computer?
Do you want to open?
The Learning Book.
Yeah. So. Okay, yeah, it's originally my fault.
Okay.
Crop it. It works.
Okay, it works. That should be good. Okay.
So don't be gentle.
Oh, really? Oh, okay. So where did you finish last time?
Just yes, we went over. Right, this is it, right? I think this is about where we stopped last time. Okay. Just a quick announcement. I know we have until the end of this month, so they're gonna keep giving us the room, and then afterwards, I'm not sure. So I'm talking to USF, and they seem like they will give us something, but it's gonna be just a smaller room. So don't be surprised if one day it'll be like this is on the third floor, like in the dark corner or something like that. Okay. Hold on for just 1 second. I'm ready when you are.
Okay. So I'll just go over the book. I'll open up a page, and then we'll read it, and then I can talk about it and answer any questions. I think if there's one thing you should take home from today is maximum likelihood estimation. So I'll go over some two examples. I'll go over some. I'll go over some two examples of how that works. Okay, so I guess last week we ended on this one. Okay, so this section talks about hyperparameters. So in the example earlier, it showed an example of polynomial fitting, and it had a single lambda hyperparameter. So let me let's see here. So for example, if you're fitting, you have some. If you have some data, and then you're fitting into a line, you can say we have f of x, and then if it's a line, you have a single parameter a, actually two, a and b. And in the example, we would write something like f of x equals ax plus b plus lambda x squared. So they give that as an example. So here you can see lambda is this hyperparameter. You want to fix it before you start fitting a and b. You fix it to some value, for instance, 0.1. Another hyperparameter is actually the degree of the polynomial. You can think instead of fitting f, you're fitting g, where g is something like ax plus b plus cx squared. And then you have lambda x. So it could be a quadratic polynomial. So the issue here is how do you select which one to fit? And normally what you do is you have something called the validation set. So what you do is you fit your model to data, you fit your second model to data with different value hyperparameters, and then you evaluate on a different set of data. And then you use that to pick your model.
example, A, B, the parameters, or lambda is a parameter, or what?
Lambda is a hyperparameter. So, right. So it's a bit of an artificial distinction, but historically there is the splitting into parameters and hyperparameters. So you don't fit lambda to data. So what would happen? What would happen with these hyperparameters? If you fit them to data, you would overfit. Right. So let's see. Let me think of a good example. So the way you would do it, you would fit this to data, and then with some value of lambda, and then you would change the value of lambda and you fit it to data again, and then you would compare on a different data set the accuracy would get. So a typical value might be something like 80% of your training data is training, and maybe 20% is validation, and then actually 60, 20, and then you have another 20% test. So can anybody see why we have 3 instead of 2? Like, why don't we choose those hyperparameters using the test data?
Because then we would overfit with the test data, like our choice of hyperparameters would maximize our test data, which might not generalize.
Right. So if you did that, what would happen? You might get good results on your test results, but then when you actually use it in production and use it on real data, you will get worse results. Whereas if you keep this test set separate and you don't actually tune any parameters with the help of it, the value you get on your test data set should represent the value you will get in your future sets. So it will actually be a realistic estimate of your future performance.
So, in other words, you are basically assigning prior to A and B, prior distribution to A and B.
To A and B, well, you're fitting A and B to data.
Yes, but I mean, effectively putting this lambda and fitting actually different functions, you effectively doing prior to.
Yeah, actually, yeah. This shouldn't be X, this should be A. So you could get something like this.
Then it's like regularization. This is different.
Right, yeah, the lambda X squared actually didn't really make sense. So this is the more common approach. So essentially you can think of it, if you're fitting high degree polynomials, if you have high coefficients, you may have some function, data is here, but then you have something that fits the data very well, and then just shoots off. So you can impose those penalties, and you're just saying, I don't want my coefficients to be really big. But you don't know what this lambda is, so you use this extra validation set to choose it.
Was that X squared word to begin with? Why are you imposing lambda on the slope and the
On the A and B? Because that's how it's commonly done. So if you want to,
if you don't want to overfit, wouldn't you want to make it the line instead of the curve? So you would impose it on X squared instead. So it would go to 0, so the X squared wouldn't.
oh, I see what you mean. Right, so you could have something like, you would just see, let's see, X squared, so you could have, maybe you don't care about this one. So you could just have a penalty on the linear term and quadratic term, or you could have a penalty just on the quadratic term. And those are all design choices, and ideally you would use you would use data to choose which one to do, and you would use a validation set. So you would have all those choices, and you would try them out, and you would pick the one with the best validation set performance. Okay. So Yes, 80% is a typical for training, 20% for validation. This feels a little bit out of date. So on large data sets, like ImageNet, people often don't do this validation. You just throw, you just make your network as large as possible and just use just a single training set. So in neural networks, people are not using validation as much. One exception when you're using validation in neural network training is when you're training, and often the graph looks like it goes up, and then it starts going down. And then you want to determine when to stop, so you pick some point. So this is the test set performance. And then the training set performance, it will continue going up. So you can go forever. So you want to pick this point. However, if you did this on a test set, people would say you're cheating. So you can never use pick your parameters based on the test set performance. And instead, you pick it on a validation set performance. And on the validation set, it may look something like this. So you would pick here. And the reason it might look like this is because it's smaller, so you may overfit earlier.
So you just have to say that on the training data set, we decide what kind of the model is, and on the validation, we decide what parameters are.
So validation, you use it instead of a test set. So if you have multiple experiments, you can run multiple CFAR experiments and then just report the best test error. And I think that's what people do in real life. But what you're supposed to do, instead of looking at your test set performance, you're supposed to look at the validation set performance and never look at the test set. And only after you finish tweaking, only then you run on your test set. But as we have seen with MNIST and CFAR and those small data sets, you have this constant creep up in methods and they don't always generalize. So for instance, with MNIST, I've tried taking the best state-of-the-art model and I tried it on another handwritten digit data set, and the 99.2% model only gave 92% accuracy, even though they're also handwritten digits. Okay, so and Ian mentions that likely we're moving to larger data sets, so this issue is not as important. Cross-validation is another thing that's mainly a property of small data sets. So what happens, suppose you have a data set with only like 100 examples. If you split it like this, you're going to train on only 60 examples and then validate on 20, which may seem like too few. So what people do is a technique called cross-validation. So cross-validation is where, so suppose you have data set with 5 examples, you essentially pick the first 4 as your, actually 6 examples. Here's your test set. You essentially pick the first 4 as your training set, and then this is the validation set. And then you create another fold where you pick, for instance, these circles as the training set and this as the validation set, and so on. So essentially you train in cross-validation in this example, you would have, for instance, 5 splits. You have 5 data sets, so you would train your model 5 times, and you would have 5 evaluations. And you would just average them together, and that will give you an alternative measure. Yeah.
People use this in, so in Kaggle it seems people build a ton of models, they do cross-validation, stack them together, do averaging, and they get high results. Is this in research as well?
I mean, I haven't really seen people do them for neural networks. It's extra engineering. You have to train, if you do 10-fold cross-validation, you have to train model 10 times more. So I haven't seen people really use that much. So right, this is the k-fold validation. So in my example, the k would be 5. Okay, so what is an estimator? So let's see. Here we see. So as a simple example, suppose I'm throwing, I have a coin and I'm throwing it and I want to estimate the probability of the coin heads. And I do something like heads, heads, tails, heads, heads. So an estimator is a function which takes these the sequence of throws and outputs some probability. So my estimator. As an example estimator, I have f to 0. It just outputs always probability equals to 1, probability of heads. So this is an example of an estimator, and if your coin is biased, it only lands heads, this estimator will be a really good estimator. Okay, bias and variance. So when we're dealing with estimators, there's an assumption, there's some underlying true distribution which generated the data. And
I really didn't see this one.
oh, really? Okay. So there's an assumption, there's some true distribution that generated the data, and we can measure the estimators by with their bias and variances. So bias is how far off you are from the true answer on average. So for instance, suppose I have a perfectly fair coin, the true here be true, it's equal to 1/2. And I have estimator 0, which always, no matter what the data is, it always says 1. So the bias here it's 1/2. Because it's the expected value of the difference between B true and the B estimated. Make sense? So he gives a more common estimator used for Bernoulli, which is, well, what's the most natural thing? If you have a coin and you're throwing it and you're getting some heads and tails, how do you estimate the true probability of heads? The most common estimator, it's called the sample mean, which is basically you count the number of heads. So in this case, we have 5 throws, we have 3 heads, so we will say 3/5. It's our empirical estimate.
Looks like you have 4 heads.
The what?
Is it 4 heads?
It's 4 heads. Yes, it is 4 heads. Okay, so, and then if you wanted to verify if it's biased, you go through this math, and you'll see that it's unbiased. And later, when we talk about maximum likelihood estimation, we'll see that this thing actually also comes out of maximum likelihood equations. And maximum likelihood estimators are known to be unbiased in a wide range of settings. So here's another example. You have some data sampled from a Gaussian, and then you want to estimate the mean parameter. So you could think of it, you have some points, and you have a Gaussian with a known variance, and this estimate is true if the variance is identity. So you basically just average all those points together, and that's your estimate of the mean. So here he talks about estimating the variance. So it's a one-dimensional Gaussian distribution. So here, this one is actually a bit more interesting in that the most natural estimator is actually biased. And you can think of it, let's see. So, as an example, suppose you have a Gaussian with mean equals to 0 and standard error equal to 1. And you sample just 2 points. So if you sample just 2 points and you use the formula, your estimate of the variance or the standard error will be biased. It will actually be smaller. So you can intuitively think about it. When you're estimating the mean and the variance at the same time, you're essentially going to be measuring, you're going to go between the 2 points and you'll measure the distance to them. And if you go through the math, that estimate will be 1/2 of what it should be. So you may notice from formulas that there's this corrected estimate of the standard error where you don't divide by the sample size, you subtract 1 from the sample size. Yeah.
So the variance for a model or custom models, what's the definition? You define the bias as being average error.
Mm-hmm.
So what's the variance? Variance of that error.
So variance is typically measured as, let's see. So bias, you can look at the estimate of the model as the data goes to infinity. So as data goes to infinity, you may have some bias left over, and then the variance should go to 0. So you can estimate the bias by looking what the estimate is when you go to infinity, and then you take, for a finite sample size, you essentially see how spread out around that estimate your estimates are, and that's your variance. So generally, people talk about bias and variance in models, and those things are well defined when you're dealing with point estimation. When you're starting to deal with decision trees and other classifiers, it's not often strictly defined. But a more general, the fuzzy definition, variance essentially tells you how rapidly your model improves as the data increases. And the bias tells you what is the ultimate limit of your model. So if you have some non-zero bias, it means that if you increase the model to infinity, the model will still not be the true model that you estimate.
Should we always try to minimize to get the bias 0?
Are we trying to get the bias 0?
Yeah.
Well, if we can get the bias 0 without sacrificing anything else, then that's the ideal thing. But often what happens, you can decrease the bias, but you will increase variance, and sometimes that's actually worse, because what you care about is the overall error. which brings us to this section. And so this is notation for the variance. Oh, sorry, standard error is the square root of variance. So here, he goes through the derivation for the variance of a standard Bernoulli estimator. So as in our example, you have a set of heads and tails, and then you count the number of heads divided by the total number of throws, and that's your estimate. And you can go through this math here to figure out what the variance is. So one thing to notice on this formula, so there's two things to notice. First of all, if you plot this this graph, it'll look something like this. 1, 0. So if theta is equal to 0 or theta is equal to 1, then variance will be 0. Then we see why. Do what?
You wouldn't observe any variations. It would be all heads or all.
Right, right, exactly. So one thing to notice is that variance is different in different parts of the model space. Another thing to notice is that it decreases with the number of samples. So as m goes to infinity, variance goes to 0. And that's a common thing that you see. And it's actually a common, this 1 over m factor is actually, it comes up pretty often in machine learning. Sometimes you see a 1 over square root of m. If you cared about, instead of variance, if you recall the definition of variance, it's the expected value of x minus mu squared. So if you instead were interested in something that wasn't squared, you would take a square root of that. So if you propagate the square root through the math, you would get this square root of 1 over m. So you typically see this square root of the data size in machine learning papers. Essentially, it says that as you increase your data set, you're off by a square root of the size of your data set. Any questions?
Let's say in this example, wouldn't it be reasonable to minimize like cross-validated error? Basically, you have 5 observations.
Mm-hmm.
You pretend that you don't see one. So you basically, if you hide the first head,
Mm-hmm.
you would see. So you would have like five estimations, and you can basically calculate the. I mean, you can actually analytically find the head that would minimize this cross-validated error.
I suspect that estimator might actually be the same. So,
I don't think so.
so you're saying you just remove one and then you compute sample average of the rest,
Yes.
and then you remove another one and you compute sample average of the rest,
Yeah, of course.
and then you average the two sample averages.
Well, if you have the true, you can compute the first of all you can find p that would minimize the sum of all the errors.
Right, by taking sample average.
No. If you basically here. So you first take, you cross out this, and then you, so usually what you do, so if you take this first out, minus 1, well, we have 3/4, right? And so according to you, you would basically calculate your error on this guy. So your error here is well, a discrete value. You would be
So one point is if you look at the entire data set and you compute optimal weights, then it's almost as you don't use any validation. So the whole point of validation is that some parts of the model don't see the validation. So I think what they're suggesting is look at the entire data set and pollute the weights going from one thing to the other. So you can take this offline.
Okay. I suspect if you went through the math, it might be the same thing, but we'll see. So this estimator, the sample mean, that comes out of maximum likelihood estimation, and it has some nice properties. It's actually the most, I think it's called UMVUE estimator, which means uniform minimum variance unbiased estimator. So essentially, it's the best estimator in some sense. Actually, let's, I may talk a bit about this. So recall the estimator earlier, you just say p equals 1 regardless of the answer. So that estimator, supposedly true, theta equals to 1. That estimator is actually really good. It's actually, out of all estimators, it's the best estimator. However, it's not the best estimator if you look at the full range of model. So this is when this issue of uniform minimum variance unbiased estimator comes in. So we may have some estimator which is best for 1, we may have some estimator which is best for 0, and in between. But we're interested in finding an estimator which is not beaten everywhere. And that's the maximum likelihood estimator. In the sense that there is no estimator which is better than maximum likelihood estimator for every setting of P. Yeah.
So this expectation is taken from the real distribution.
Expectation, which one?
So the expectation is over the true distribution.
This one. Yes, real distribution.
But in reality, we don't know the true distribution. That's what we are trying to
Right. So in reality, you always estimate. You have some empirical estimate of your variance. And one way people do this is by bootstrapping. You essentially remove parts of the data from your training set, and then do this estimate, and then you remove a different part of your data. So you keep doing this, and this gives you some estimate.
So your explanation of bias and variance was that it changes over the model space, but isn't it that like bias and variance are like intrinsic to a model? So like neural networks have lower bias, higher variance, and like decision stubs have like high bias, low variance.
Right.
So how does that work?
So for point estimation, you may have, let's see. So a bias and variance are properties of an estimator. So you can think of a different model having a different estimator. So you're saying that neural networks in general have lower bias?
I mean, in literature that you read about, say like bagging, bagged decision trees was supposed to be like really good at some time because they were like decision trees had the property of overfitting and therefore like higher variance. And so you would bag them across several trials and that would produce variance. So that would imply that decision trees, like a fully built out decision tree, has higher variance and lower bias. Whereas the decision stub is kind of the opposite.
Right. So I'm guessing in those claims there is an implicit assumption of some kind of an atypical model or averaged over models, because here imagine you're trying to estimate this p parameter and the true value is 1, so you're always getting heads. Your variance is 0. You use bagging, you do not reduce variance. So whenever people say reduced variance, they're probably assuming like a typical model for like a typical region for the space. It's over there. The display only shows over there. Oh, really? Oh, okay.
But it's essentially.
I think you need to go up. Oh, because the screen was off actually. Yep. Okay. So, in point estimation, you really care about this value, which is how far off you are from the true value on average. And if you expand this equation, you're going to get that it's the sum of the bias squared plus variance. And this is the thing that you really care about minimizing if you care about estimating something like probability of heads. So here you can see driving bias to 0 is not necessarily the best thing. The best thing is driving the mean square root error is the best thing, mean squared error. So if you reduce bias, but by virtue of that you increase the variance, that's not a worthy trade-off.
So this bias versus variance stuff applies mostly for mean squared error or other loss functions?
So it's the most straightforward to explain for the mean squared error, and there are actually papers trying to generalize it to other loss functions, but none of them are actually straightforward enough to pick up popularity. So you can find it, but people don't use too much. But it's a nice thing to keep in the back of your mind. So in this example, you can see if you do this penalty for this lambda, if you increase the lambda, your A's and B's are going to be shrunk towards 0. So if you're estimating it, you may be estimating it here. You increase lambda, suddenly they're clustered around here. So that decreases their variance. But it may also increase their bias unless the true values are 0. So this is always like the theme that comes up in machine learning. You cannot, I think earlier there was the Snow-Fibonacci theorem. So there's always this trade-off between bias and variance. So if you're doing something to your algorithm where it suddenly requires less data to learn, you are sacrificing something. You're essentially programming something into your algorithm where it will actually learn better on your data, but you can always craft another domain or another data set where that same algorithm will actually perform worse. So there's always this trade-off. There is no universal way to decrease the amount of data you need to learn. So there's this graph, which was part of the slides. Let's see. Yeah.
So I was reading some slides from John.
Mm-hmm.
So he proves that this until non-regularization is basically assuming a Gaussian trial on
Mm-hmm.
this.
Yeah.
And so he even suggests that we can actually find a value of lambda by assuming a variance of data divided by variance of weights.
Mm-hmm.
So what I could not understand was how do you choose or how do you find out the variance of weights before doing any experiment?
How do you find the variance of weights? Why do you need to know the variance of weights?
Because, for example, if you have a prior on the weights,
Mm-hmm.
that your weights are all very close to zero,
Right.
that would mean that your lambda is very big.
Mm-hmm. Right.
So lambda is inversely proportional to square of inversely proportional to the variance of prior on weights.
Mm-hmm.
So if you assume a variance is too big, that amounts to a small lambda.
Right.
So, but I could not understand how should I choose that variance at the start of experiment.
I see. Well, most likely answer is that people just guess. There is always like this favorite lambda or favorite nu that everybody has, and they just start with it, and then they change it over time. There's some parameters. For instance, if you use Atom Optimizer, there's 3 hyperparameters, and they were just set in TensorFlow, and most people don't even change them. So there's a lot of theoretical justifications, and also in practice, people often just have something that just worked before. Let's see. Right. So this graph, this is sort of a symbolic representation, which you can see several things going on. So capacity here is how many things the model can represent. So the capacity in the polynomial example, it could represent, for instance, how many terms you have. So if you have lots of terms, the variance, if you have variance and reduce it to a single number, you would essentially, you would sum up over all the variances of all the coefficients. So variance of some G of I, where G of I estimates the ith coefficient. So you can see is if you have more coefficients, you have more terms in the sum, all the terms are positive, this variance goes up. But also, another thing you see going on here, the bias is increased capacity, the bias goes to 0. And this means there is a theorem in calculus that any function can be represented as a polynomial with enough terms, if it's a nice function. So this means that if you keep increasing the number of terms, eventually, no matter what your true function is, eventually you're going to fit it perfectly with enough data. Then there's this red line, the generalization error. You can see it goes down and then it goes up. So again, a common demonstration is with polynomial fitting. If you have, for instance, 4 points, and you use a polynomial with 4 terms, you can always fit this data perfectly. But what happens is it will fit the true data poorly. So if you have your true data set has 5 points, and you fit the 4 points with the 4-term polynomial, the 5th point is probably going to be very far off. So there is some kind of a sweet spot where you can reduce the capacity of your model, so the number of terms in your polynomial. It will make your model fit your data worse, but it will make that same model fit the future data better. So that's a trade-off to keep in mind. And whenever you are in a situation where you're fitting data and you are fitting it really well, then sometimes you should be suspicious and you should think, why am I fitting it so well? If it goes to 100%, maybe you're overfitting.
So is capacity just adding the bias and variance together and minimize it out with some weighted average of the two?
Is capacity just what?
Just adding the two and try to minimize the bias and variance, like just a constant way on each of them, or is it with some weighted average of the bias and variance? Like, are there any scenarios where you might care more about the bias so much about the variance. You might want to try to.
Well, you typically want to care about just one number. If you have, so you want to like combine all the things together into a single number, which can be the squared error, for instance. So you don't want to care about 3 different numbers because then you can't choose what to optimize. But what was the question? The question is, what is capacity?
Yeah.
Okay, so capacity is, in my example here, capacity is the number of terms in your polynomial. More generally, capacity is, it tells you how many different models you are able to represent.
My question is actually, what is, so in that figure would be, what is the generalization error?
Oh, okay. Generalization error is the error on data which was not used to choose the parameters. So it's essentially a test error. So you fit your data, you fit your function on some parameters, and then you evaluate it on some future data which you did not use for fitting. So generalization data is what you actually care about the most.
Well, this figure looks like it's biased plus variance. I think that's kind of a coincidence.
In your example with no data, when you had like divided by number of samples minus 1, so actually if you minimize the square root of error for variance, you were supposed to divide by n plus 1, but no one uses it.
Yeah, so that could be an example where it diverges. So you may care about, if you care about squared error, you may actually not want to divide by n minus 1. But okay, consistency. So consistency is basically the idea. It has some mathematical definition, but what it comes down to is that if you have enough data, you will recover the true model. That is the definition of consistency. And they have one example, and there's some connection between consistency and asymptotic unbiasedness. So asymptotic unbiasedness just means if you have more and more data, the bias becomes smaller. And the example they give where asymptotic unbiasedness is not the same as consistency is if you're estimating, so you're estimating the probability of heads by just counting the number of heads in the first row. So in that example, that estimator is unbiased. Therefore, it's also asymptotically unbiased. But it is not consistent because it's only using the first data point. So as you increase the size of your data set, the estimator does not increase. So it still gets your model wrong most of the time. All right, and I'll can finish up with this maximum likelihood estimation.
Actually, if you can use like this side, I think it will be a little bit easier.
Oh, okay.
I'm worried that if somebody's streaming it, they like literally don't see anything over there.
Okay, so one may think if you're estimating things, how do you come up with the estimators? And in the case of heads and tails, there was this obvious estimator, but it may not be so obvious for other models. And then there's the general principle called the maximum likelihood estimation, which essentially tells you how to come up with these estimators. So in our example, suppose we have heads, tails, heads, heads, tails. We're interested in, so we have some model which says with probability P, P get heads. So in order to define our maximum likelihood estimator, we have to determine what the likelihood is. So likelihood is another word for probability. Technically it's slightly different, but you can just think about it as probability of the data. So we have this parameter P. What is the probability that we obtain this sequence of heads and tails? So we assume that we throw them independently, so the probability of getting heads in the first one is P. Then we have tails. Since they add up to 1, it's 1 minus P. Then we have heads again, it's P. Heads again, P, and then it's 1 minus P. So that's the probability of obtaining this data sample. You can rewrite it, and you can say it's P cubed times 1 minus P squared. So maximum likelihood estimation says you take your data set, you find the probability of it with your parameters, and then you try to maximize it. So essentially, the P that we want is the P that maximizes this this quantity. So in practice, it's much easier to work with logarithms, and because logarithm is a monotonic function, you can always replace this quantity with a logarithm of the quantity, and it doesn't affect the result. So we can say this is argmax of log of P cubed 1 minus P squared. And then we use properties of logarithm to rewrite it as argmax 3 log P plus 2 log 1 minus P. So let's see. What?
Take it to YouTube.
Right. Exactly. So we have this quantity. So that's the, let's call it F, argmax of F of P. So we're interested in finding where F of P equals to 0. So we get 3 over P plus minus 2 over 1 minus P. So that's the derivative. So F prime of P. And we have to set it to 0. F prime of P equals to 0 implies 3 over P equals to 1 minus P. So we get 1 minus P over P equals to 2 over 3. What is algebra? How does it work?
3 minus
What?
3/5.
3/5? Okay. P equals 3/5. Okay. All right, and that's you have 3 heads in there. But basically, that's the general principle. You just have some model with some parameters. You express your data set. You find the probability, and then you solve for the parameters which maximize for the probability. And you end up with some nice formula. So if you do this for a more general case, where instead of having a 3 heads and 2 tails, you have something like x heads and then out of n examples, when you go through the math, you would say that E is equal to x over n, which is the empirical estimator. Good. Okay. Any questions? Right, it's been an hour, and I can go through really quickly.
No, we should keep going. We're like not nearly done. We have another hour. Just to let you know. Brace yourself.
All right. That's, Bayesian. So it talks about Bayesian estimation, but I want to skip that point.
Why?
It's not that popular nowadays. Supervised learning. Okay, so what are the supervised learning algorithms? So it talks about logistic regression. If you work through the math, you can find logistic regression is a form of maximum likelihood estimation. So essentially, the assumption you're fitting, you have some data set. You have some data set and you're trying to fit the line through it. In an earlier lecture, you saw that there is this. Earlier lecture, we talked about fitting lines to data, and then there was this minimum square estimator. There is an alternative way of obtaining it using the maximum likelihood estimate. So he talks about it later. Somewhere he talks about it. But the point is that you're essentially trying to, you make an assumption that your points are sampled from a Gaussian distribution around the predicted mean, and you're essentially trying to maximize the likelihood. If you recall, the Gaussian distribution, probability of x given some mean, is proportional to actually a logarithm of the probability is proportional to negative x minus mu squared. So essentially, when you're maximizing the product of probabilities, it's the same as maximizing the sum of the log probabilities. So you can see that you're essentially dealing with the sum of squared errors. So you use this connection to derive this minimum squared error criteria.
Are there any questions about like supervised learning? That just more general questions about supervised learning? There's one.
So there's this K-nearest neighbors algorithm. Does the analysis of bias versus variance and generalization kind of apply to K-nearest neighbors? Because those seem more weird. Like they just, it's more like a dictionary of your data.
So, K-nearest neighbors to refresh memory. You essentially, for instance, you have a 2D data and you have some circles, and then you have some crosses, and then you have a new data point. To determine the class of the data point, you're for k equals to 1, you essentially find the closest neighbor, and you are saying what the class is, and the class here would be x. For k nearest neighbors, you're finding, for instance, k equals to 3. You find 3 nearest neighbor, and then take the majority class. Does it have bias and variance? Well, it seems like it's unbiased. Yeah, I'm not sure actually. Seems like a weird one. So the notions of bias and variance, they're like here they're derived through the point estimators, and this is a non-parametric method. So
You can estimate it by cross validation.
you can estimate the error, right?
And
How would you separate the error into bias and variance? It seems, let's see, bias and variance. Okay.
but in general, it's hard to separate, to decompose.
Right. It feels like something that people may have.
You should use your own. It's like a 10-step process.
Oh.
I mean, intuitively, if you think of bias as like the distortion of what the model can be, in k-nearest neighbors, it can essentially be pretty much anything. It doesn't have to be a plane, a line, or anything. Simply because like the decision boundary that's created by can be of any shape. But that would also have like a higher variance if you also think about it, because it's really unstable at any point could really cause a huge shift.
Right.
Like that boundary. So in that sense, I can see why that would be like the case. But if you have infinite data, you can also like if you got the entire distribution, then you've got a very solid understanding of what like the decision boundary would be.
Yeah. Actually, it makes sense to talk about it. If you increase k, imagine if k is really large, then you're unable to represent sharp changes. Essentially, if k is the whole data set, then you will essentially predict the majority class always. So, but you will have a very low variance. So as you increase k, your bias increases. So you're favoring more smooth examples. Okay, then there is this thing called support vector machines, which was really popular 10 years ago. And if you went to NIPS, it was actually probably the most popular topic for all the papers there until it went back to neural networks. And support vector machines, I think one reason they're popular is that there is this, they're kind of beautiful mathematically, and all of the research around them is centered around this thing called the kernel trick. So the kernel trick, so here's a description of it. So essentially, the kernel trick says that it gives people a way to represent this linear classifier by this sum here. And the way you come up to it, intuitively, you can think of it, how is this W obtained? So W is your optimal weight. So if you look at the gradient descent, when you're doing gradient descent, your gradient descent step, so like W nu is equal to W plus some value times X times some other factor. So essentially, when you're doing gradient descent, you're constructing your W by summing up various data points with various factors in front of it. So you can, and then more generally, you end up with this equation. And what you can see here, the kernel trick is they're saying, well, here we're just using a regular dot product between two x's. What if we, instead of using a regular dot product, we use a fancy dot product? And it turns out, if you use some other fancy dot products, it is equivalent to projecting this x in a higher dimensional space than taking a regular dot product there. So this is like this mathematical connection, and people wrote lots of literature exploring it. In practice, what this looks like is that your classifier, when you have a support vector machine, you essentially, it's sort of similar to nearest neighbor in there. You essentially have this point and then there's some number of special points called support vectors, and then you evaluate your similarity between your current point with these support vectors and the coefficients, and then from there you extract your classification. So in a way, the support vector machines are these fancy nearest neighbor algorithms. Right, but they haven't really been popular recently. Okay, what are the other supervised learning algorithms? Let's see, there's k-nearest neighbors. There's decision trees. So I guess, do people use them in Kaggle a lot?
Decision trees.
I don't, yeah, they, I think they use boosted trees. Yeah, boosted, mixture of boosted trees or something. Gets most, for most problems where deep learning doesn't win, they use.
I think even for deep learning, it's useful to stack multiple nodes, because you can always then sample multiple nodes.
Yeah, like stack them with decision trees? Like have a decision tree decide which model to use?
Something like that.
And also they have multiple ones, so they get that they can kind of average across or even do better weighting between the multiple decision trees. So they, so they can do really complex models that get like your 0.5 precision gains and make you win the contest. That are very, you can't understand what's going on. And also I think like in big companies, when they were doing ranking functions or in ads, when they were trying to do, I think first they were using logistic function to do classification, but when you need that boost in precision, you would do a mixture of decision trees. Which is
Yeah, sounds like Microsoft really likes decision trees.
We use decision trees
Oh, for what?
for relevancy.
what?
So for relevancy algorithms that we're using for our search, like to predict like what's the most relevant search for the user, we use decision trees, like graph trees.
Actually, on that point, does that scale really well? Like, is that performance effective? Because I've heard logistic regression is significantly faster.
This is like still in like a babyhood, so we're gonna see. It's like still like A/B testing, but yeah, that's because the data is not very complex. It just makes more sense.
Okay, so decision trees, he brings them up. I guess the picture is pretty self-explanatory. You basically here, it's a decision tree in a space with two attributes, and you can think of it. The first split is on y, so it says if y is greater, then you go in the area above. If y is less, you go into the area below. And the second split is on x. So in the top area, x is split here. In the bottom area, x is split here. So it goes on recursively. Okay. So next, he talks about unsupervised learning algorithms. So a core example of unsupervised learning algorithm is this principal components analysis. And I think I talked about it earlier, but principal component analysis is a sort of a canonical algorithm to get the correlations in the data. So here's an example, which is related to earlier example. Suppose your data is sampled from Gaussian distribution with a covariance maybe 0 and covariance like 2, 1, 1. So this means that probability of x1, x2 is proportional to log probability. It's proportional to x1 squared plus x2 squared plus 2 plus 2 x1 x2. So if you see a formula for the likelihood like this, you can sort of tell that these terms are entangled. So there's this cross term here, x1 and x2. So what this means, if you actually plot, if you sample from this distribution, it's going to look like this. So it's essentially sort of tilted to the side. And another way of saying these coordinates are entangled is that you know if, for instance, you know the point is far off on the x-axis, you also know it will be high on the y-axis. So that's the notion of entanglement. And principal component analysis is a technique which lets you take this data set and essentially extract this correlation structure. So the way it works is you can take the empirical covariance matrix, so that's the true covariance matrix, an empirical covariance matrix, maybe something like 1.8, 0.9, 0.9, 1.8. So you take the empirical covariance matrix of this data set, and then you find eigenvectors of this data. So if you do this on this data, the eigenvector, the primal eigenvector would be something like this, and the second one, they have to be orthogonal, would be something like this. So essentially, once you know these eigenvectors, you're able to decorrelate the data. So you know, knowing these eigenvectors, you know that you can rotate or determine a new set of axes where the correlation is missing. So that makes learning better. But alternatively, you can use that to discover that there's this principal component, and it shows that some coordinates are correlated. So I guess in so a common application of finding correlations, people doing gene analysis, they're interested to know if some gene expressions are correlated with each other. So they're trying to extract the correlations from data. So that's unsupervised learning. So he gives two ways of extracting those eigenvectors. So one, you can compute this variance matrix here. So this is my empirical covariance matrix. If you actually wanted to compute it from data, you would use this formula over there. So X is your design matrix. So design matrix, in my case, it would look like, transpose, it would look like this. So you have two coordinates. So you have some value 1, 2, 3, 2.5. So you essentially have 2 columns and 0 rows. So that's your matrix X, and that's the design matrix. And you can use this formula to find the empirical covariance matrix, which is here. And he uses, he shows that you can get this eigenvectors. You can either compute this matrix and you find the eigenvectors of the matrix, or you use another thing called the singular value decomposition, and you take the original data matrix X, and then you do a singular value decomposition of that, and you also can extract eigenvectors from there. It's the left, right singular vectors. But I think in practice it's not a great idea because your covariance matrix in this case is 2 by 2, so it's tiny. your data matrix is kind of huge, so you're running single value decomposition on a huge matrix. So depending on implementation, it may be slow. Right. Another unsupervised learning thing, which is actually, this one is actually pretty useful in real life. It's called the k-means clustering. Yeah.
There is an intuition behind PCA, something minimizing distance, projections.
Yeah, so the intuition behind PCA is you want to find, let's see, so the first principal vector, you want to minimize the mean squared error. So you essentially want to minimize, let's see. So you want to find vector W, first new vector, and you're interested in minimizing, let's see, W projected. So you're interested in projecting each data point onto W. So it's like X W, and suppose it's normalized, times, let's see, so it's W, so like this, minus the true value X times W. And you're minimizing it to X. So the intuition is you're trying to fit a single line through the data set that will
Minimize the distances of the points,
right.
If you put from each point you draw a line that is perpendicular to your fit.
Right. Right. And then to find the second one, you can essentially, there is a technique called shrinkage or something like that. So you basically can remove this, you can subtract this coordinate from your data, and then you solve this problem again. So you can iteratively find all the eigenvectors in this way. There is the k-means clustering, which is pretty useful thing. So does everybody know what k-means clustering is? Okay, not everybody, so I'll explain. So essentially, suppose you have some data set and you have some points, and essentially you want to cluster them. You want to figure out that these points are in cluster 1, these points are in cluster 2. So k-means clustering is this very simple algorithm. Suppose if you know the number of clusters, you will initialize with some seed, some 2 seeds. So you initialize, and it consists of 2 steps. So first step is for each seed, you suppose this is seed 1, and this is seed 2. For each data point, you assign which cluster center it's the closest to. So here, this is all 1, 1, 1, 1, and then maybe this is 2, 2, and this is all 2. And after that, you compute the new center, the new centers. So here you see these things are 2s. So now my 2 is now here, and my 1 is now here. And then you recompute. Then for each point, you find the closest points to each center, and you use it to label each point. And you iterate, and this is surprisingly simple algorithm. It doesn't work that bad in practice. So if you ever want to find clustering in your data, that's like the first thing to find. Yeah, actually. You define like the mean, so it will be over here. Which ones? Yeah, so these ones, this one will become 1. Yeah, so it actually gives good results surprisingly often. think there was a, let's see. Well,
And how would you estimate K? Just estimate how would you come up with this?
right. So one approach people use, they just try for different values. So you can try for different values, but the problem is you can try for different values and then compute the error. So you can see on average how far each point is from the cluster center. But if you use the more cluster centers you use, the error becomes lower. So yeah, I guess there's actually quite a bit of research in finding K. There's some algorithms which automatically choose it over time, but they're a bit more complicated.
So on Scikit-learn website, there are some useful metrics to find out, to figure out what the best value of K would be.
Oh.
Sylvester scores and
Which scores?
Sylvester scores.
Sylvester scores.
You can use Scikit-learn. Very convenient.
I see. Yeah, so there is some formulas you can plug in. Essentially, there's some the information criterion approach. They basically give you a penalty for the K you use. So you compute your error and then you add the penalty, and that essentially tells you. It essentially estimates the future, the generalization error. Okay, this is opinions. Okay, and then I guess I agree with this one. It's kind of a weird place to put this because it's not necessarily an application. It's something that's used for everything. So here it just goes over how to do SGD. So I think we covered it mainly in optimization. Does anybody have questions about stochastic gradient descent? One issue he brings up is the issue of the loss decomposing. So a very nice property when you're minimizing, when you're training your model, you have some function that you're minimizing, and it's a very nice property if this function is just a sum over training examples. And that's true for most applications you have. One example which is not true, the Andrew Ng, they had this unsupervised feature learning class, and they're training this autoencoder, and the loss was the sum of like the errors over x or y plus a special term called sparsity. So essentially, it tried to fit the data, and at the same time, it wanted each neuron to be activated 10% of the time. And that's an example which doesn't decompose over the training sets. Yeah.
Isn't that the same thing as like dropout? And when you apply dropout on like, you can use dropout with batch learning on gradient descent, can you not?
We'll drop out with batch learning. Well, this is just a penalty. So what I'm saying is that sometimes people use a cost function which doesn't decompose over the examples.
Okay.
So if you wanted to, for instance, train a neural network which fits data, but you also wanted neural network to be on average, some activations are 10% active. So, and you have a penalty of how far off you were. If you like write that as a sum, you can't decompose it over examples.
And you can't use stochastic.
Right. So batch normalization is another weird one. So if you use batch normalization, it essentially depends on your batch size. So technically it doesn't decompose over your examples either. Okay. So he's talking how gradient descent is typically not respected. But what happened with neural networks, there is no better alternative. So you just use SGD for everything. Right, so before the deep learning, people were really into support vector machines and used this kernel trick, which is what support vector machines do. But the downside, as I mentioned, support vector machines are essentially glorified nearest neighbor methods. So, so they don't scale as well with the size of the data set. So in particular, it scales quadratically with the size of the data set. Okay, and then let's see. There's two more sections. Section is how to build a machine learning algorithm. So the recipe. So there is a recipe. So the recipe is you have a data set, a cost function, and the optimization procedure, and the model, actually, 4 things. So a cost function in all the examples before. So for instance, if you're doing linear regression, your cost function is a squared loss. You're essentially maximizing over I, something like mu of I minus x of I squared. So that's an example of a cost function. Another example, when I was fitting this Bernoulli model, I was maximizing log probability. That's another example of a cost function. So I was maximizing the sum over, well, sometimes it's known as the log likelihood. And optimization procedure, once you have a cost function, you have to decide how to optimize this cost function. And the most common example is using stochastic gradient descent. Or you may decide, if you have a small data set, you may decide to use one of the second order methods like LBFGS. But typically, for neural networks, typically you just use stochastic gradient descent, and the main choice is which variant of SGD you use. So you can use something like Adagrad or Adadelta. There's actually a pretty entertaining video by Siraj about different optimization algorithms. So I think I recommend. Do you guys know Siraj?
Yeah, you should put his like YouTube channel name as a bookstore.
Well, anyway, you should look it up. Actually, I thought it was quite well informed. And then, and then the model. So you choose the model. So in this example, the model is just the model with a single parameter p. Here, if you're fitting data, the choice of the model is like what order of polynomial you use. Do you use linear regression or use a quadratic regression? Right, so that's the example. He uses the cost function is the log of the probability. However, if you expand this normal distribution, it will come to maximizing the sum of squared errors. So your cost is actually a squared loss. So you may add additional terms. So typically, with linear regression, you try to make your coefficient small. That's the L2 regularization. Right. In some cases, yeah.
What is cross entropy fit?
Right, so cross entropy, you can actually view maximum likelihood of a special case of maximizing cross entropy. So, let's see. So actually he talks about it a bit in the chapter. I'll give an example. So, as an example of the coin, you have an empirical distribution. You have the p hat, which is 3/5. And I'm interested in finding p. So I may be interested in minimizing KL divergence. So an alternative way of deriving this estimator, I minimize the KL divergence, and the order is important here, of p hat. P hat given p. So if you look up the definition of KL divergence, it's equal to expected value of p hat log p hat divided by p, which we can expand it. It's expected value of p hat log p hat minus p hat log p. And then you notice we're minimizing it, so the p hat is actually constant. So this term, it doesn't matter what it is. There is no p is not a part of it, so you can remove it. So it's the same as argument of negative p of p hat log p. So essentially, if you take this approach, it's equivalent to the maximum likelihood approach. So the KL divergence approach, you think of your data distribution, and you think about the distribution that you are modeling, and then you're trying to minimize this distance between them. And it is the same as maximum likelihood estimation. Yeah.
So this expectation is over the estimated distribution.
Yeah, it's estimation over p hat.
So the p hat should not be decided. So the p hat times log.
Let's see, should it be? Oh, yeah, maybe actually, let's see.
No, I mean,
Yeah.
the p hat log p hat over p. The first p hat should not be there.
This one?
Yeah.
Why not?
Because the expectation is already.
Oh, I see what you mean. Oh, okay, yeah. Yeah, I was actually, I guess it would be more correct if you did something like this. Right. Yeah. Right, and then he talks about sometimes you need a special case estimator, special case optimizer, such as decision tree, because you can't use gradient descent. However, people really like gradient descent, and I've seen cases when they take application which uses a special case estimator and shows how to use gradient descent. As an example, earlier I talked about k-means. People actually show that k-means can be formulated as minimizing a special kind of loss using expectation maximization, and then people actually have a gradient descent estimator to do the same thing that k-means does. Okay, challenges, last section. Okay, well, there is the, let's see, recursive dimensionality. So one intuitive way of talking about curves of dimensionality is if you increase the number of parameters, the number of configuration increases exponentially. So if you use a very bad algorithm, the amount of data it may need may theoretically also increase exponentially. However, in practice, people are able to train neural networks with millions of parameters if it's deep enough and not really hit this. But with point estimation, that's something that comes up. So the second challenge, I guess, is regularization. People have to figure out how to regularize things. So in the example of polynomial regression, you may fit something, and then typically if you fit it, your tails are kind of like shooting to infinity. And you may have an assumption that things don't change too fast. But people are still figuring out how to encode this smoothness assumption in other models. Okay. This was also in the slides. So if you have, if you want to visualize the area, so if you have a nearest neighbor classifier and you have some data points here, so you can visualize the region. You can visualize the region of the space which gets the label 4, and it's known as the Voronoi diagram. So here, if we use a nearest neighbor classifier, all the points closest to 4 will get the label. So essentially, it will look like this. Does the diagram make sense? Should we break?
No, I think we're like literally 5 pages away. Maybe we can just power through it so we can close this chapter. I'm not looking
Okay.
forward to making another chapter 5.
All right. Let's see what else is there. Manifold. All right, so this was also in the slides. People often think about data lying on some lower dimensional space. So you may have, for instance, images. An image like 1,000 by 1,000 pixels, 1,000. You can think of it as a point in a 1 million dimensional space. However, the set of all possible images, people like to think of them as lying in some smaller dimensional subset. So you try to fit this with maybe a neural network or some other model with 10p parameters. So essentially, you can think of it as finding this lower dimensional manifold to fit it. And that's an idealized diagram. So here, you have a two-dimensional space, and you have some data, and you're fitting this one-dimensional manifold through the data. So in the manifold learning algorithms, that's a form of unsupervised learning. Okay, so, and the example for images, if you actually sample images at random, you are going to pretty much get noise. So let's use this sort of evidence that natural images lie on the submanifold. So if you just look at the space, most regions of the space, they don't contain natural images. So natural images are actually a very small subregion of the space, and people think of it as a manifold rather than some disjoint set, because you can take a natural image and you can modify it slightly and it still remains a natural image. So for instance, in video, the subsecond frames are pretty close to each other, but they still remain in this natural image manifold. Okay, talks about.
I wonder if in practice, in the previous graph, one one.
How would you do this in practice?
How do you use practice?
Well, the one method which is not very good is you just define a parametric model and you try to fit it to data. So, and then there's a whole range of manifold learning algorithms which are different. So essentially, actually in this example, what you really need is if you find, for each point, if you find its neighbors, you may be able to connect it. So actually, this manifold learning algorithms, they often try to find this connectedness graph. So for each point, they find neighbors, or they try to find some connectedness structure, and then they go from there. But I haven't seen many practical algorithms. Some of them use this. So the problem is, if you connect to too few neighbors, you're not going to discover the structure. If you connect to too many neighbors, it's not going to be one-dimensional anymore. So what people do, people connect to some large number of neighbors, and then they use the smart graph algorithms, like spectral clustering or various graph algorithms to prune those connections, and they tend to be typically quite expensive. Right. And this is example of this images, and this would be a two-dimensional manifold. So a person is turning left, right, or up and down. So you can think of these images lying on the manifold described by these two angle parameters. And ideally, you want to have an algorithm which can discover it. If they discover this manifold, then possibly you can extrapolate and can generate new faces or like new angles which you haven't seen before. All right, so it looks like with this, you're prepared to embark upon your study of deep learning.
Questions? Concerns? There's one question over there.
So, like one note on the, I guess, autoencoders and GANs are examples of other things that try to find this manifold.
Yeah, I think anything that has parameters and tries to fit the data can be seen as manifold learning, because you can adjust those parameters, and that gives you different results.
The second question is how do we apply this bias?
It's your headset. Something is wrong.
Oh, sorry, what was the second question?
So this bias versus variance and model capacity. It seems for deep learning the capacity of the models is pretty high, so you would get maybe bias 0.
Right. So
any practical advice into how to apply this intuition to actual models?
So the complications with deep learning is that there's no longer a clean separation between your model and your optimization algorithms. So a classical study of bias versus variance assumes you can you have this deterministic procedure which obtains the optimum each time. But in neural networks, you actually don't obtain that optimum. So this wisdom right now is why neural networks don't overfit so much, is that gradient descent just is not able to optimize it so well. And essentially, you can have neural networks with millions of parameters, and if they have enough layers, they don't overfit. And one suspicion is that because the stochastic gradient descent doesn't actually optimize very well, that constrains its capacity. So you may have a neural network with lots of parameters, but actually the capacity is not that great. Yeah.
So when you have an intuition that bias or variance is your problem, then you should use regularization to fix one of the.
Well, if bias is a problem, it's typically, you can see it as underfitting. So you train it on your data and you're getting bad performance on your training data. So you should always get at least decent performance on your training data, because that's sort of, you can't get better performance than on your training data. It's kind of like your ceiling. So if you have bad performance on training data, you have too much bias, and you should maybe make your model larger. And if you have variance, too much variance. So too much variance is essentially when you don't have enough data to get good results. So if you have a data set which is not big enough, then you may be interested in increasing the bias, like adding extra assumptions. So like in a neural network, you may be replacing your fully connected layers with convolutional layers. So that's an example of adding bias. Because if you replace with convolutional layer, there's this data set, well, there's MNIST, but then there's also permutation invariant MNIST. So once people thought MNIST is too easy, they started permuting pixels in some deterministic way in all the examples, and then trying to get the good results there. So if you use convolution on that example, it's actually going to make things worse. However, if it's not permuted, the convolution will make things better because the bias is actually correct in that case. So you should always add as much bias as you know about. If you know something about your domain, you should always bring it in.
Could you elaborate more on how the convolutional net adds bias in that case?
Yeah, so convolution on that. Essentially, when you have a convolution, your filters are shared. So you're saying that filter in all the positions, they should be the same filter. And that makes sense because if you look at typical images, the filters that it learns, it may be edge detectors. So essentially you have an edge detector here and an edge detector here. However, if you randomly permute all the examples, those assumptions break down. So you no longer have, your best filters are no longer edge detectors, and you may have a different best filter in this position, may be different from that position.
So you're randomly permuting only on test and not on training?
No, everywhere. You have a deterministic permutation, and you apply it to all the example, training and testing.
But won't it still learn the same edges? Like, won't it learn edges for that particular data set?
Well, it wouldn't learn edges per se because edge detector is a property of natural images.
Yep.
If you take random image, the edge detector is no longer good. And when you take MNIST and permute the data, those look like random images. It destroys the spatial correlation in the data.
Okay, yep.
So there is a new kind of structure, and essentially you can think of convolution. Convolution is equivalent to matrix multiplication, where some of the parameters are tied. So essentially you have like P, and then you have Q. So essentially you have a matrix multiplication, and your assumption is that you should use this structure. If you randomly permute or deterministically permute the things, you can think that the structure is also permuted. So essentially, the new equivalent structure, it may just look different. It may be like some other things are tied. So you still have tying, but it doesn't correspond to convolutional tying. It's some other kind of parameter tying.
I have read people doing data augmentation flipping them horizontally, vertically.
Mhm.
So, but convolution let's still work good even with data computation.
Mhm.
So what you are saying is opposite.
Well, what I'm saying is for permutations. So essentially what permutation does, you just permute the pixels, and what happens when you permute it,
Okay,
it no longer looks like a natural image.
I see.
It looks like a random image.
Okay, you mean pixels within image are just permuted.
Just to a random position. Right, so and those data augmentation actually, data augmentation is actually a very useful technique. So there is many smart mathematical techniques people invented, and then when I was at Google, we always tried augmentation first, and then some intern would come and try to beat it with the latest paper, and it was very hard to beat. So augmentation is actually a really good technique.
Maybe we actually have to. They actually started telling me that we have to leave. So maybe we can wrap this up, and we'll be going to town hall. So if anybody wants to grab a beer with us, feel free. Oh, where are they? Yeah. Yeah. Are you? Let's see.